Okay, today we're going to be going over a review for a Calculus 3 final. So the first question we're doing is Lagrange multiplier to find the point of a cone, which is z is equal to the square root of x squared plus y squared, which is closest to the point of 4, 0, 0. So as a little refresher, to find our Lagrange multiplier, we set our gradient of f as equal to the gradient of g, and then we have our constraint of g is equal to k. So for this example, we want our f of x, y, and z equal to our point from our cone, which is our x, y, and z, and then we want to subtract our point that we want to find the closest to, which is 4, 0, 0. And then we're going to square it. And this will give us our point that we're looking for, which is going to be our x minus 4 squared plus y squared plus z squared. And this is going to be our f of x, y, and z. So now we want to find what its constraint is. So we want to find our g of x, y, and z. But this is going to be our cone formula, which, if you look, is z is equal to square root of x squared plus y squared. But to get rid of the square root, we just set z squared is equal to x squared plus y squared. And since we want our constraint to equal a k, meaning that we don't have any variables, we just put z onto the other side, giving us 0 is x squared plus y squared minus z squared. So when we find our g of x, y, and z is equal to x squared plus y squared minus z squared is equal to 0. So when we find our gradient of f is going to be equal to the partial of x, partial of y, partial of z, which will be 2x minus 4, 2y, and 2z. And then our gradient of g is going to be equal to 2x, 2y, and then negative 2z. So when we put this into our equation of the gradient of f is equal to the lambda times the gradient of g, this will give us 2x minus 8 is equal to lambda 2x, 2y is equal to lambda 2y, and then 2z is equal to lambda 2z. So the easiest one to go with is 2y is equal to lambda 2y, because if we bring this lambda 2y to the other side, we get 2y minus lambda 2y is equal to 0, which gives us 2y and then 1 minus lambda equals 0, meaning that either our lambda is equal to 1 or our y is equal to 0. And then we will do the same thing for our z function. We will have it as 2z is plus lambda 2z is equal to 0, which gives us 2z, but this time is going to be 1 plus lambda, meaning that lambda would be negative 1 here. And don't forget to write the constraint at the bottom of x squared plus y squared minus z squared equals 0. So now we'll do our last Lagrange, which is our x. So if we bring it over to the other side and bring our 8 to the right side, this will give us 2x minus lambda 2x is equal to 8, which gives us again 2x 1 minus lambda is equal to 8. So the easiest thing to start with here, once we have all our equations set up, is check our y, because either y could be 0 or lambda is 1. But I'll do it in a different color. If we have lambda equaling to 1, this means that 2x minus 8 is equal to 2x, which just isn't true, which means that lambda can't be equal to 1 and that y is equal to 0. And since that's the case, we can check this formula up top to find our x, because this will become 2x, 1 minus negative 1, because we're going to take our lambda equals minus 1, is equal to 8. And then we will have divide both sides by 2, so x, and then this will be 2, is equal to 4. So x is equal to 2. And now this is where the constraint comes into play. Because we have y equals 0 and x equals 2, we have enough to solve for z. So this will become 2 squared plus 0 squared minus z squared is equal to 0. And as you can see, our 2 squared is going to be equal to z squared, or z is going to be equal to 2, meaning that x is equal to z. So that is going to be our first point, which I'll write at the bottom. Point of 2, 0, and 2. And then we need our other point that would solve the constraint, keeping y at 0, which is going to be when x, y, and z all equal to 0. So our second point is going to be 0, 0, 0. So now that I've cleared up some space, we're going to find f of 0, 0, 0 by putting it into the original equation, which will give us a 4. And then we're going to find our f of 2, 0, 2, which gives us square root of 8. Because this equation is the squared version of all of them, meaning this would be 16 and this would be 8. But since we want our regular version, it's just going to be 4 and square root 8. And since square root of 8 is less than 4, the point of 2, 0, and 2 is the closest to the point. Okay, so for question 2, we have suppose that a is bigger than 0 and b is greater than 0, and we want to use polar coordinates to find the volume of the solid bounded by the cylinder x squared plus y squared is equal to a squared, and the plane z equals 0, and the paraboloid z is equal to ax squared plus b. So if we draw this out, we'll have our z-axis, our y-axis, and our x-axis. And we're going to get the points, we'll get the graphs. Our z is 0, meaning that it can't be, it has to be greater than 0 for z. And that our point of our cylinder is going to look something like this up to a paraboloid. And then it has to be above the plane z equals to 0. So the first thing that we're going to want to do here is we're going to look for our bounds of r, z, and pi, since we want it in polar coordinates, but we're going to do it in cylindrical coordinates to make it a little bit easier. So what we're going to do is our r is going to go from 0, which is our inner point, to the radius, or the outside of the cylinder. which is a. So r is going to go from 0 to a. Then our z is going to go from 0 because that's the lowest it can be, and our z is going to go up to the paraboloid because that's the top bound. So it's going to go from z to a x squared plus b. And then finally, because it's a full cylinder and we can go all the way around the origin, our theta is going to be 0 to 2 pi. So our equation is going to look like the volume is equal to 0 to 2 pi, 0 to a, and then 0 to, because this is an x and we have to change it to polar coordinates, this will become a r squared cos squared theta plus b of r dz dr d theta. So this will then become 0 to 2 pi, 0 to a, and since there's nothing to go off of, it'll just become our upper bound, because when we're integrating it by z, it'll just become z, which just becomes our point, which will be a r squared cos squared theta plus b times r dr d theta, which will give us 0 to 2 pi. And then we're going to have a r cubed cos squared theta plus b r dr d theta. So where that comes from is just implementing the r from the r d theta into the equation. And we're still taking the integral from 0 to a. And now this will become 0 to 2 pi of a times a to the 4, so that's going to be a to the 5 divided by 4 cos squared theta plus b a squared divided by 2 multiplied by d theta. So our next step is going to just be splitting up the two integrals, which will be a to the 5 over 4 multiplied by the integral from 0 to 2 pi of cos squared theta times d theta plus b a squared over 2 from 0 to 2 pi times just d theta. So this then will become a to the 5 over 4, and then using trig identities, we could do 0 to 2 pi, 1 plus cos 2 theta over 2 times d theta, and then since there's nothing to integrate here, we'll just go by the bounds, which will be b a squared over 2 multiplied by 2 pi, and the 2's will cancel there. So now this will give us a to the a5 over 4 pi plus pi b a squared, and then our final answer can be written as pi a to the 5 over 4 plus pi b a squared. And if you're wondering how to simplify this, you just take the 2 out and do a u sub here. But if you want to skip ahead, cos 2 theta from 0 to 2 pi always just equals to pi. So our next question is asking for a sphere of radius 2 is centered at the origin. A hole of radius 1 is drilled through the sphere with the axis of the hole lying on the z-axis, and we want to describe the solid region that remains, and then we set up the integral without integrating it. So again, we'll have our x, z, and y, and then we will try to draw this area. So the first thing we're going to do is draw the sphere, which looks something like that. And then we're going to draw our cylinder of radius 1, which will look like that. Roughly. Very roughly. So setting up our bounds of integration, the easiest ones to do is our theta, because we're going to use cylindrical coordinates here. So we know off the bat that because it goes all the way around, our theta goes from 0 to 2 pi. The harder ones now are our z and our r. But if we write out the equation of a circle, we'll have x squared plus y squared plus z squared is equal to 2 squared. And then x squared plus y squared is equal to 4 minus z squared. But if you notice, this just becomes r squared due to cylindrical coordinates, which will be 4 minus z squared. So our r is going to be the square root of 4 minus z squared. And then, because our r starts at the end of the cylinder and goes to the edge of the circle, this is going to become 1 to r to the square root of 4 minus z squared. And then finally, we want to find our z value. But our z doesn't go to the very top of the sphere, so we can't just use the radius. It goes to this point, which is messed up due to the cylinder. So the way to do this here is we're going to set either our x or y to 0, because that will find when we'll be at our maximum. So if we come up here and we go x squared plus y squared is equal to x squared plus y squared plus z squared is equal to 2 squared. And since when we're going to be at a maximum, our x or y is going to be equal to 1, since that's the radius of the cylinder, we're going to make this 1 squared plus 0 plus z squared is equal to 4. So z squared is going to be equal to 3, and z is going to be equal to square root 3 plus and minus. So that is what our z will be bounded by. -3 to z to positive root 3. So setting up this integral will look like 0 to 2 pi, negative root 3 to positive root 3, and then 1 to root of 4 minus z squared, r dr dz d theta. Alright, so now our fourth question is, let C be the curve in the three-dimensional space defined by the vector function r of t is equal to e to the t cos t, e to the t sine t, and e to the t. So we want to reparameterize this curve with respect to the arc length measured from the point 1, 0, 1 and the direction of increasing t. So we're going to set s of t as equal to the integral of 1, 0, 1 and r of t, and then we want the absolute value or the length of dr. So since dr is equal to the magnitude of dr with respect to dt multiplied by dt, we need to find our dr over dt, which is just the derivative of our function. It's an r, which is going to be equal to e to the t cos t minus e to the t sine t, and then it's going to be e to the t sine t plus e to the t cos t, and then just e to the t. And then since e to the t is in every single term, we can factor it out to make it e to the t, which would just be cos t minus sine t plus cos t, and then 1. But if you notice, we need the magnitude of dr dt, not just the derivative. So now we need the magnitude of dr over dt. And since it's going to get all terms squared and square rooted, we can just take out the e to the t, because it would just become e to the 2t, but square rooting it just keeps it as e to the t. And now this will become a long square root of cos t minus sine t all squared plus sine t plus cos t all squared, and then plus 1 squared, which is just 1. So now this just becomes e to the t, a long square root of cos squared t minus 2 cos t sine t plus sine squared t plus sine squared t plus 2 cos t sine t, and then we'll continue the square down here because it's too long, and then cos squared t plus 1. And if you notice, we're going to cancel a lot of terms here. So first things first, our negative 2 cos t sine t cancels with 2 cos t sine t, positive. And then we're just going to be left with cos squared t plus sine squared t. And if you notice, that will just become 1. And then again here, we'll have sine squared t plus cos squared t. So that just becomes 1 again. So after that long square root, we just get e to the t multiplied by root of 1 plus 1 plus 1, which is just root 3. So now, when we have our s of t, this is just going to become the integral of whatever t value gives us 1, 0, 1 up until our increasing t. So if we look back to our original function and find where it is equal to 1, we'll notice that if we set our t equal to 0, our first term and our original one of e to the t cos t will become 1. If we set 0 into e to the t sine t, that will become 0. And then if we set a 0 to t as e to the t, that will just become 1. So it will become 0 to t of e to the t root 3 times dt. And then again, we can just take out the root 3, and since the integral of e to the t is just e to the t, we can skip all the way to the bounds of 0 and t, which will give us root 3 of e to the t minus 1, because that's e to the 0 is equal to rs. And since we want to reparameterize it, what we need to do is make this s equal to rt, and then we replace rt with our original function. We replace the t in the original function with our new variable of s. So to solve for t, what we need to do is we need to set s divided by root 3, so divide both sides by root 3, is equal e to the t minus 1. Then we can get s over root 3 is equal to s over root 3 plus 1 is equal to e to the t. And then if we take ln of both sides to get rid of the e, this will become ln of s over root 3 plus 1 is equal to t. Now, the whole point of this was to change our r of t into r of s. And we're going to put this into our original function, so not the derivative or the magnitude, the actual r of t. So since we can factor out the e, this will become e to the ln of s over root 3 plus 1, and then it will be cos of ln of s over root 3 plus 1, and then it will be sine of ln of s over root 3 plus 1, and then 1. However, if you notice, e and ln cancel, just giving us s over root 3 plus 1, and then cos of ln of s over root 3 plus 1, sine of ln of s over root 3 plus 1, and then 1. And this is what our reparametrized curve will be. So now for part B, when we want to find the line segment of the curve between t equals 0 and t equals 1, the only difference here is in our integral, instead of going from 0 to t, we're going to go from 0 to 1. So all it becomes is 0 to 1 of e to the t root 3 times dt, which is just root 3 multiplied by e to the 1 minus 1. Or s of 1 is equal to root 3 multiplied by e minus 1. So next up we have question 5, which is asking to find the average distance from the point r0 to the points of the circle of radius r centered at the origin. So if we were to draw this, we'll have our x and y axis because it's only in 2 dimensions, and we're going to have the circle of radius. And then we're going to have our point of r and 0. And we're trying to find the average distance. So if this is our x, we're trying to find the distance between these 2 points. And as a reminder, the average is equal to 1 over b minus a multiplied by the integral from a to b of f of x times dx. So the first thing we want to do is, since it's a circle, we're going to want to use polar coordinates. So we're going to have our x as r cos theta and our y as r sine theta. So now our distance, as you can see, is going to be the Pythagorean's theorem because we made a triangle. So we're going to have the square root of this distance here squared multiplied by the height. But as you can see, the height is just y, but our distance here is going to be r minus x because we only want this little segment. So this becomes r minus x squared plus y squared, which if we put in to our square root, we're going to get r minus cos theta squared plus r sine theta squared. And now expanding this, because we can factor out an r, this then becomes 1 minus 2 cos theta plus cos squared theta plus sine squared theta. I'll add that. But since the cos squared theta plus sine squared theta is equal to 1, this leaves us with just r, or the square root of 2 minus 2 cos theta. But as you can see in the hint, it says that 1 minus cos of alpha is equal to 2 sine squared alpha divided by 2. So if we take our r and we change this to 2 and 1 minus, this will just become cos theta. We can change this to being equal to r 2 multiplied by 2 sine squared theta divided by 2, which this then becomes 2r sine of theta divided by 2. So that's what our function of d is going to be. So now what we want to do is we want to take our function of 2r sine theta divided by 2 and we want to find the average of it. So since we're going to be using polar coordinates and we want to find an average in terms of r, we're going to make this function in terms of theta. So we're going to have d theta. So since it's a circle and our angles are going to be consistent, we're going to choose our bounds to be 0 and 2 pi. So we're going to have 2 pi minus 0, and then the integral from 0 to 2 pi of 2r sine of theta divided by 2 times d theta. Now if we make some space, we can change this. Since we can factor the 2 out, which will cancel, we get 1 over pi, and then it just becomes the integral of 0 to 2 pi of sine of theta divided by 2 times d theta, which we will use a u sub for. So we set u is equal to theta divided by 2, which would make our du is equal to 1/2 d theta, which means 2 du is equal to d theta. So now this will give us our 2 factored out, 2r over pi, and then it's the integral from 0 to 2 pi, because we'll change it back into theta before putting in our bounds, of sine of u multiplied by du. Then we will get 2r divided by pi, and the integral of sine u is just negative cos, so we get negative cos, but because I didn't change the bounds, we have to change it back to theta divided by 2 before we put in the 0 and 2 pi. Now this will just give us 2r over pi multiplied by negative 1 minus 1, which will give us our final answer of the average being 4r over pi. Now next up, we have question 6, which is consider a particle that moves counterclockwise around the circle centered at 0, 0, and a radius a at a consistent angular speed of omega radians per second, and show that a, the velocity vector of the particle, is tangent to the circle. So we're going to start off with a diagram, just like normal, and since it's again just a circle and it's centered at the origin, so we have our circle here, and we're going to have our velocity of r. We're going to have our position vector of r. So we're going to try to find a velocity vector that is perpendicular to r or tangent to the circle. So we have our original, which is our position vector, which is r of theta, which is a cos theta and a sine theta. And this is because if you look, we have our cos theta and our sine theta, which makes up our position vector. So now we want to find our velocity vector. And if you remember, our velocity vector is just the derivative of our position vector. So this is going to become negative a sine theta and a cos theta. So since we want it in terms of t, this is going to become negative a sine theta, but because we have to do the chain rule, we need to multiply it by d theta over dt, and then it's going to be a cos theta multiplied by d theta over dt. But in the question, it tells us what d theta over dt is, because that is our constant angular speed, which is omega. So this gives us negative a omega sine theta and then a omega cos theta. But something to note is that our unit vector of r is actually equal to cos theta and sine theta. And then our position vector of theta is equal to negative sine theta cos theta. And you can make sure that they are perpendicular to each other, because if you take our unit vector and multiply it by our theta unit vector, this gives us 0, meaning that they would be perpendicular to each other or a tangent. So if you look at our question, we want to make sure that our velocity vector is a tangent to our position vector. But if you look at our position vector of r of theta, this just becomes a multiplied by our r unit vector. And then our velocity vector just becomes a multiplied by omega of our theta unit vector, which means that they are tangent, which means that our velocity is tangent to the circle. Now part B is asking for the speed of the particle, and we want to make sure that the speed of the particle is a multiplied by omega. But the speed of the particle is just going to be our v, which is equal to the magnitude of our velocity vector. But if you look here, our velocity vector is just a multiplied by omega multiplied by the unit vector of theta. So if we have our a omega and our unit vector, to take the magnitude, we have to square and square root our function. But if we square and square root this term, this will just become a squared square rooted, which just becomes a, and then omega squared square rooted, which just becomes omega. But if you remember what unit vectors are, when you take the magnitude of a unit vector, since it's a unit vector, it's just equal to 1, meaning that our speed is in fact just a omega. Now for part C, we want to show that the acceleration of the particle is directed opposite to its position vector and its magnitude is a omega squared. So to do that, what we need to do is to find our acceleration, which is equal to the derivative of our velocity vector with respect to t, which is a times omega, and then it's going to be negative cos theta, and that will be multiplied by the same thing. Since we have to do the chain rule, it's going to be omega, and then it will be negative sine theta multiplied by omega. Now if we factor out the omega, this makes us a omega squared and negative cos theta, negative sine theta. And now if we take out the negatives, this will become negative a omega squared just multiplied by the r unit vector, meaning that this is oppositely directed than the position vector, because the position vector is going to be pointed up and to the right, while our acceleration is going to be down to the left because of the negative sign there. But now we're not done, because it wants to also show that its magnitude is a omega squared. So we want to take the magnitude of our acceleration, which again is just going to be the magnitude of negative a omega squared and the unit vector. This is just going to become a because it's squared, so it's going to be positive, and then omega squared doesn't change, and again, because it's a unit vector, its length is just 1, so it's going to be multiplied by 1, which satisfies the question, making it just a omega squared. So our final question is: a particle is moving counterclockwise around the ellipse x squared over 9 plus y squared over 4 is equal to 1, subject to the force field F is equal to negative 2yi plus 3xj. And then we want to write the line integral represent the work done by the force field F in moving the particle once around the above ellipse. So we're going to start off by drawing our ellipse. So we have our x and y going from 3, 3, and negative 3, 3, 2, negative 3, and negative 2. So it'll look like that. And we have our angle, and we're moving counterclockwise. So our x squared over 9 plus y squared over 4 just becomes x over 3 squared plus y over 2 squared is equal to 1. Now, in order to make it under one parameter, we could change it all into polar coordinates, but that would turn out to be really messy. So instead, what we're going to do is there's a little trick for ellipses where you can just make your position vector equal to whatever the denominator is, so 3, and then change the top to cos theta because it's x, and then change our denominator again to sine theta. So instead of an r for polar coordinates, it just becomes the denominator. And then our angle, because it goes around the full ellipse, it goes from 0 to 2 pi. So we want to find the work done going once around the ellipse of our function multiplied by dr. So this means we will get the integral from 0 to 2 pi. And then we're going to have our negative 2 because of the force field, but we have to change our y to 2 sine theta. And then we have to change our 3. Instead of x, it's going to be 3 cos theta. But now we need to multiply it by dr. In line integrals, dr becomes dr over d theta times d theta. So we need to find what our dr over d theta is, which in this case will just become negative 3 sine theta and then 2 cos theta. So this becomes the integral from 0 to 2 pi of negative 2 sine theta and then 9 cos theta multiplied by negative 3 sine theta, 2 cos theta, all multiplied by d theta. So this works with the dot product. So it's going to be our first two terms multiplied together, added by our second two terms multiplied together. So this then becomes the integral from 0 to 2 pi of negative 4 sine theta multiplied by negative 3 sine theta, which is going to be 12 sine squared theta, plus, and then 9 times 2 is 18 cos squared theta, multiplied by d theta. So now what we can do is we take this and split it up. So we get 0 to 2 pi of 12 sine squared theta plus 12 cos squared theta plus 6 cos squared theta times d theta. Because this term will just become 12, because if you factor out 12 and then sine squared plus cos squared becomes 1. So now this just becomes the integral from 0 to 2 pi of 12 times d theta plus the integral from 0 to 2 pi of 6 cos squared theta times d theta. And since this just becomes theta, it'll just be our bounds. So it's just going to be 12 times 2 pi plus 6 times, and then if you remember from the previous question, our cos squared theta from 0 to 2 pi just becomes pi. So we get 24 pi plus 6 pi, giving us our final answer of 30